All right.
What number do you have?
Well, you just need to hold it up over. Right here. All right, now, let's hold it back a little farther. All right, because you guys are going to need to see, but feel free to reposition yourself if you need to.
What
Okay.
number do you have?
Number 2.
That's number 2. Number 2, thank you.
Okay, turn it a little bit toward me. All right. All right. So start out by reading it, if you would, please.
Determine the final velocity of the cart, assuming that there is no friction, is part A.
All right, so you have a cart. It's at the top of a hill. You're going to release it from rest. And you want to know how fast it's moving at the bottom of the hill.
Yes.
All right, go ahead.
So because we're at the top of the hill, we knew that that the energy started in gravitational, and then it ended moving, which we're solving for the velocity. So we knew that that would be kinetic energy. So we first started by solving for the gravitational energy. So it's mgh. So it would be 0.5, which is the mass of the cart, and then g is always 10, and then times 0.2, which was our height. And then that gave us 1 joule of energy. So then we plugged that into the kinetic energy equation. So we knew that it was 1 joule of energy was equal to 1/2 of the mass, which was 0.5. And then we're solving for the velocity, and that's squared. So if you would have to multiply by 2 on both sides to get rid of the 1/2. So then 2 equals 0.5. Then you divide out 0.5, giving you 4 equals b squared. Then you take the square root, so b equals 2 meters per second.
So what I like about this is, if you look at their bar charts, because that's the thing that's important here. What do you notice about the height of the gravitational energy on the left and the kinetic energy on the right? What do you notice about those two bars? They're absolutely the same height. So she was able to solve for the gravitational and set that equal to the kinetic. Now, the second part of this is really interesting. It says, while rolling, it loses 10% of the energy. What's the new speed? Okay? So let's look at this one. Tell us what you did here that's different than the original, because this is excellent the way that they structured it.
So we knew that the gravitational and that the first bar graph would be the same. So we knew that we started with 1 joule, and we knew that we were going to lose 10% of that. So that would be 0.1 joules of energy lost to thermal. So then if you add that together, or you subtract that from the gravitational, giving you your kinetic energy, which would be 0.9 joules.
So look where the structure is here. In green on the left, there's 1 joule of gravitational energy. And on the right side, you can see that out of the system, in red, they lost 0.1 joules. That's the 10% that was lost. And then if you lose 0.1 out of 1, how much are you left with? You're left with the 0.9. And then you use 0.9 and you plug in, you solve. And so what is your new speed?
Oh, it's going to be 1.89 meters per second.
And what was your speed without friction?
2 meters per second.
So if you add friction to your system, do you think you're going to be slower or faster with friction?
Slower.
Slower. And does your math bear that out?
Yes.
How's that look? Well, I mean, these take a little bit of practice. Okay, these take a little bit of practice, but I think that this is instructive in terms of how they did what they did. I think it looks good. All right, thank you. You can erase that. All right, what's the next one say? All right, what number was this?
3.
What number?
3.
3. Owen, can you read 3 for us?
A 0.4 kilogram block is placed on a spring and compressed at 0.2 meters. After it is released, to what maximum height does the block reach? And how fast was the block moving when it was at half its max height?
So let's do the first part first. Okay? It says a spring is compressed by a block. They let it go. It gets shot up in the air. To what maximum height does it go? That's the first question, right?
Mm-hmm.
All right. So tell us what you guys did.
Well, there was elastic, energy only, so
because of the spring.
it's like we just did the elastic equation, which is 0.5 times the K, which is 320 newtons per meter, and then times the X for the, yeah, how did we get that?
Which one?
For the K? What is the 0.4?
Oh, that was the mass.
Oh,
wait.
why is it, oh no, it was the D, which is 0.20 squared, which is 0.04.
Good, so look at that closely, okay? Look at that closely. The elastic energy formula is 1/2 K x squared. And so it says that it was compressed 0.2 meters, but when you square 0.2, you get 0.04. Do you guys see that?
Mm-hmm.
All right, so what's the total amount of elastic energy?
6.4 joules.
Good. So you have 6.4 joules to start out, yes, of elastic. Where does all that elastic energy go?
It turns into kinetic as it's going up. Well, when it stops at the top, it turns into gravitational. So
Sorry.
it would just be all gravitational for the next bar chart. And we would have to calculate that. So since we didn't lose any energy, the EG would equal would be 6.4 because they're the same height. And then we would plug in 0.4 for the distance, and then 10 for the gravity, and we would have H, and then we'd solve for that.
So 0.4 is the mass. 10 is the gravitational field strength, not the gravity, right?
Oh,
It's
yeah.
it's the gravitational field strength. And you solve for the height, and the height was what?
It was 1.6 meters.
All right. So this is good. Okay? 1.6 meters. Is that cool? All right. Now, there's a second part to this. It says, once you solve the first part, you got 1.6 meters. It says, what was its speed when it was halfway up? Okay? What was the speed when it's halfway up? So this time, all right, if we're looking for the speed when it's halfway up, how are your bar charts different for the second part?
So when it's halfway up, it would be like half gravitational, half kinetic. So we took the elastic and just cut it in half and put each half in kinetic and gravitational. So then that value would be 3.2 because the elastic would be 6.4. So we cut it in half, it would equal 3.2, and then we plugged in for EK, 3.2 equals 1/2 times 0.4 times velocity squared, and we just solved for velocity and got 4 meters per second.
So this looks great, okay? Where the first, on the left side, it was all elastic going to all gravitational, but on the right side, it's all elastic to start, and it's half gravitational and half kinetic in the end. And they're able to use that kinetic energy, right? They solve for how much kinetic energy, and then they were able to say like, oh, if I have this much kinetic energy, what's the speed? That looks great to me. Questions for them? All right. We're actually going to run out of time, so let's stop for now.